Welcome back to Norton theorem. Now, Norton theorem and Thevenin's theorem, as you already know, they are basically the same theorems, really. Like, they are the same thing. They have the same method and they kind of have the same outcome. The only difference between them is that one of them will give you, instead of giving you the source and the resistance or inductor in series, it will make it in parallel instead. And that is the only difference between them. Now, I would put Norton theorem and uh, Thevenin's theorem together in the same video. I could do that, especially since they are both short, because this will be a short video, so there are only 2 examples on it, because for how similar they are with each other. But it doesn't feel fair. Like, I would rather have 2 separated half-an-hour videos instead of having 1-hour video with both of them inside of them. So anyway, let's get started. Now, again, we mark in the zone that we need to separate. So we need to separate this side of the circuit from this load resistor here, RL. So first off, we can see that Z1, this here will be R1 plus XL because they are in series. So Z1, that will be equal with R1 plus JXL, and that will be equal with 6 ohms plus J8 ohms. And if you convert that, will be 10 to the angle of 53.13 degrees. Alright, now next, Z2, that one will be equal with this capacitor here value, which will be minus JXC, that's equal with minus J10 ohms. Alright, and then we have Z1, we have Z2. We can redo the diagram and simplify it. So here is the source, E plus minus, and here will be Z1, and here will be Z2. Alright, and these 2 sides will be open because they are for the Norton. Alright, and again, the first step is to calculate the total resistance. So we are going to draw something like this. Z1, it's exactly the same as Thevenin's. This one will be Z2, opening here, and then this one here with the red will be the replacement for E, because this one will be replaced with the short circuit, and here will be the ground. Alright, and we need to find the value for Zn. Now, how do we find the value? Where there's a junction in here, so Z1 and Z2 are in parallel, therefore Zn would be equal with Z1 multiplied by Z2 divided by Z1 plus Z2, and that one would be equal with 10 at an angle of 53.13 degrees times 10 ohms at an angle of minus 90 degrees. And let me put this one a bit lower so you can see out of the page. There you go. And then we divide this value by 6 ohms plus J8 ohms minus J10 ohms. Alright, and then that will be equal with 100, then that says 100, and 53.13 minus 90, that will be at the angle of minus 36.87 degrees. Then divided by 6 minus J2. Then Z will be equal with square root 6 squared plus 2 squared, that will be 6.325. And then the angle would be equal with 10 to the minus 1, and that will be 2 over 6, and that will be equal with minus 18.43 degrees. Alright, so then therefore 100 at an angle of minus 36.87 degrees would be divided by 6.325 at an angle of minus 18.43 degrees, and then the answer would be 15.81 at an angle of minus 18.44 degrees. Alright, Now the next one will be, we need to convert this one from polar form to rectangular form, because this will become an to become a capacitor and a resistor. So x is equal to 15.81 cos minus 18.44, that's equal to 15, and y is equal to 15.81 sine minus 18.44, and that's equal to minus 5. So then Zn will simply be equal with 15 minus J5. Alright, so that's Zn. So already very fast and very simple. Let's go to a new page because I don't have any more space. Oh, look at that. It's even simpler to find the current. So to find the current, we'll put the source in here, which will be E plus minus, and then we have the value of Z1 here, Z1, then here will be Z2, and then here will be the ground. Then don't forget about the opening as well, here and here, and what we need to find is the value going from this way to this way of IN, the current IN coming that way. Now, and this is the current I1, the current that's coming in. Now, you may think like, well, how do we calculate this current? There's no resistance in here. And that's exactly the point. Because there's no resistance in here, then there will be no current flowing through here. So then all the I1 current will simply go in I2. So then Z2 doesn't have anything to do with the circuit. It simply became an opening in here. So it might also not exist. So the only value that is Z1. And this made the problem a lot easy and very fast, because now we can just say IN, this value here, would be equal with I1, and I1 it's simply equal with E, the source, divided by Z1, the only resistance that affects the current. So then that will be equal with 40 volts at an angle of 0 degrees divided by 10 volts at an angle of 53.13 degrees, and that will be equal with 4 at an angle of minus 53.13 degrees. And there we have it. We have now the IN value. Now the last step that we have to do, and it's kind of an optional step, but it doesn't really make sense for you to not do this step, is to simply redraw the circuit with the IN values. So now, instead of using a voltage value, we are going to use a current value. So the current source will be I, and that will be of 4 amps at an angle of minus 53.13 degrees. Also, there will be the value, there will be Zn, here Zn, and beyond these 2 points here, it will be the RL, the resistance load, RL of 12 ohms. They are all connected, and here will be the ground. And to write this one in form of components with components, then we simply need to do this. IN would be equal with 4 amps at an angle of minus 53.13 degrees. Here is the current source, here is the ground, okay, and then a capacitor, because it's a value of minus, oh, I forgot to write it here. This one is supposed to be 15 minus J5. So because minus J5, there will be a capacitor XC with the value 5 ohms. And the real number 15, that one is a resistor. So there's a resistor here, R, and this one will be 15 ohms. And they are connected together here. And then the only one left is the resistance load, RL. And that's equal with 12 ohms. And here is the opening, or it can be here as well. It doesn't really matter. It's basically the same thing. Alright, so that's the solution. This is the circuit simplified. So we simplify the circuit here into this version here with the Norton theorem. I prefer Thevenin's theorem, to be honest, because I don't really see the purpose of doing this, and also we both know that it's a lot harder to calculate resistances in parallel compared to resistances in series. But if you want to solve it this way, and if you want to like use circuits this way, that's fine. I don't know, maybe there are some special cases where you prefer to have some components like this in parallel, maybe, because then maybe you can like control here and put the resistance here, and then the voltage will be the same across all of them, perhaps. I'm not very sure, but anyway, that's the way I did it. Now I'll pause it here, and we are going to go to the next one. Okay, so this will be the last exercise for Norton as well. Again, only 2 exercises, pretty short, because again it's very based on superposition, and it's also very based on theorems. Anyway, so what we need to find in this one, well, I decided why not we try to use this component in here as a reference while we have all of these other components, because you don't really always need to pick a component that's at the end of it or a component that's isolated in parallel. You can pick literally any component to calculate it, and I want to show you that. And again, it's only one current source or one voltage source, again, because if I try to do so with 2 of them, I would need to apply superposition to it, and you already know that. What I'm trying to do with these videos is to show you how to simplify a circuit, because again, you don't use Norton and Thevenin's theorem to calculate an entire circuit, you use them to simplify a circuit. Now maybe in DC you do use them to calculate an entire circuit, but here you already use them to like simplify it, because again, you usually use them with potentiometers. Use Norton and Thevenin's with potentiometers, because you'll take one component as reference, and then after calculating everything, you can just plot the number of the resistance into the formula, and then you do get the answer that you want, like the voltage or the current going through it. But we won't get into this, so let's get started. Now, because this is the component I want to know, then we need to find out the entire circuit. So we can make these 2 values, R1 and XC1, into one Z value. So then Z1 would be equal with R1 minus JXC1. That would be equal to 4 ohms minus J8 ohms. Z2, on the other hand, will be this value here, R2, and it won't be in series with this one, even though we use this component as a reference. If you look at the circuit, this component here and this opening is still real, so this is still a junction. So then we can combine, we can say those 2 are in series if there is a junction in here. Now, because even though we ignore this component, it still does exist. So R2, so that will be equal to 2 ohms, and then Z3 will be the leftover component, which will be the inductor here. So it will be XL, and that will be equal with JXL, that will be equal with J10 ohms. Alright, now we can redraw the circuit like this with the Z values. So here will be the current source, I is equal to 6A at an angle of 0 degrees. This will be Z1. This one here will be Z2. This one here would be Z3. And then let me draw it red. This here will be the opening. And yeah, let's just leave it as the opening for right now. And then they are all connected to each other, to the ground, which is here. Actually, I'll draw it here as well. There's the ground. It doesn't really matter, because if the ground is not here or any specific place like in here or something like that, then you assume that it will be at the end here. Anyway, okay, so now this will be how the circuit looks like in Z values. So now we need to calculate their values. First off, we need to calculate the entire resistance. So then we can simplify the circuit as, remember, this will be an open circuit, because it's a current source, and current sources are open circuits. They are not short circuits like volt sources. So then this one will be Z1 here, this one will be Z2 here, and then this one will be Z3 at the top, and the opening will be here at the bottom, and the value will be here, Zn. Alright, and it's all connected together to the ground, this way, and here is the ground. Now let's see what we have here. So we do have, so this is opened, so and this is opened, so there is nothing between those two. But even though this is opened, we need to find the Zn value inside this zone, so this one will still be a junction. So because there is nothing here and here, then Z1 will be instead of Z2, so we need to add them together, and then we need to calculate their parallel value with Z3, and then we'll find Zn. So a formula that we use would be Zn would be equal with Z3 multiplied by Z1, parallel with Z1 plus Z2. No, wait, I can actually do it straight away, okay. And then this one would be Z3 plus Z1 plus Z2. I forgot I can do that. I forgot how to do it. I'm looking at my notes and I saw that. I was like, why did I do that? First I should add them together, but then I realized, oh wait, I can just do it straight away. I can just apply the parallel formula straight away as long as I add those two together. Okay, so then Z1 plus Z2 would be equal to 4 ohms minus J 8 ohms plus 2 ohms. That would be equal to 6 ohms minus J 8 ohms. And that would be equal to 10 at an angle of minus 53.13 degrees. Zn would be equal with 10 at an angle of 90 degrees multiplied by 10 at an angle of minus 53.13 degrees. This value here for Z1 plus Z2. All of it divided by J10 plus 6 ohms minus J8. Again, their value together. Okay. Now this will be equal with 100 at an angle of 36.87 degrees divided by 6 plus J2. Okay, now the next step is simply to convert this value here into a polar form. So then Zn would be equal with 100 at an angle of 36.87 degrees divided by 6.325 at an angle of 18.435, and that will be equal with 15.81 at an angle of 18.435 degrees. There you go. So the Zn value that we have would be 15 plus J5. Alright, funny enough, it's the same as the previous one, previous exercise, but instead of minus J5, this plus J5. Oh no, wait, it's what? Is it 15? Actually, let me check. It's very accurate if you understand what I'm saying. Let's see here. So 15.81 multiplied by the cosine of 18.435. Yeah, it is 15. It's 14.99867. So I guess I can just put 15. Okay, now we don't have space on this page anymore, but don't worry, we are almost finished, because now we just need to find the value In. So let's redraw the circuit. There will be the current source. There will be I equal with 6A at an angle of 0 degrees. Z1. This one will be Z2. And then this one will be Z3. Okay, and this will be a short circuit here. Sorry, I shouldn't put like, I'll just put like this. There you go. And this will be IN, like this way, and they are all connected to the ground here. So it's going this way, now so this way, and this one we'll call it just I1. Alright, now again, very simple. So we just need to find the current I1, the current going through here, but also remember that I3 here doesn't really make any difference because there is no current going through it. Why is there no current going through it? Well, like the previous exercise, this IN creates a short circuit, so then all the current will go through here. So this resistance doesn't really exist. This is just a wire going this way. Now, what's left? Well, what's left is the current source here, and it's also the values Z1 and Z2, which these two are in parallel because there is a junction here. Now we need to find the current going through Z2 because that will be the current going through IN and I1. So again, we can solve it very simply by just applying the current divider rule. So then IN will be equal with I1, and that one is equal with Z1, this value here, multiplied by I, divided by Z1 plus Z2, current, divider rule. Okay, and then that will be equal with 4 ohms minus J8 ohms multiplied by 6 amps divided by 6 ohms minus J8, and then that will be equal to 24 minus J48 divided by 10 and an angle of minus 53.13 degrees, and that will be equal with 53.67 at an angle of minus 63.44 divided by 10 at an angle of minus 53.13 degrees. And then the final answer would be 5.367 at an angle of minus 10.31. And we don't really need to change it to rectangular form because this one will be used for the current source, IN. So we don't need to change it. Now we can redo the diagram with the new values that we have. Therefore, this one here, that will be IN, and it will be 5.367 at an angle of minus 10.31 degrees. And then there will be the Z value here, Zn, that will be 15 plus J5, and then it will be in parallel with the capacitor here, XC2, the capacitor that we used as reference, 14 ohms. Okay, and then all of it is just connected here at the bottom to the ground. Nice. Now we can also rewrite it where you use these values as components. So then let's see here, IN, which equal with 5.367 and an angle of minus 10.31 degrees. Current source here, and then this one will be a resistor, then this one will be an inductor. There you go, connected together. And remember about the capacitor that I used as reference. So here is the capacitor. That will be XC2 at 14 ohms. This one will be 15 ohms, and this one will be 5 ohms. The value of R and the value of XL. Alright, and this is our final circuit. We'll get something like this. And again, we can, not only that we can simplify big circuits, but we can also pick the points that we're going to simplify them from, which will be here. And this is the end of the video. And if you follow from the beginning, from episode 1, then congratulations, you now know all the basics about electronics. And what do I mean by all the basics? well, you know how to find the values inside components of DC components and AC components. And now, because thanks to you, I know as well. Because I don't think I would have studied AC circuits if I wasn't like posting these videos, wanting to cover all the basics. Okay, now I'm not sure what I'll do next, because I was thinking maybe I should do power in AC circuits for another episode, like explore power inside circuits more, or maybe I should do filters, because that one sounds very interesting as well. And also I was thinking about doing amplitudes as well and resonance. So I'm not very sure what I'll do next, but don't worry, because I think it's another few basic things, and by basic things I mean like things that are the basic that will be used in other subjects for like higher stuff, because I don't think you really need to worry about filters when doing these simple basic AC circuits, and I don't think I need to worry about resonance again when I do this type of circuits. Anyway, but don't worry. So by the end of episode 30 on the electronic lectures, we officially finished all the basic when it comes to types of circuits, and we can calculate these types of circuits. I'm very excited for the next video as well now. So yeah, thank you for watching, and I will see you next time with another video, and hopefully we will eventually get to transistors and op amplifiers. Okay, goodbye.